Fission reactors are surrounded by thick concrete shields to protect workers from the radiation produced inside. Remember that nuclear fission reactors like this harness the heat generated by fission reactions in fuel rods. But these fission reactions also produce harmful types of radiation. The neutrons that cause chain reactions can potentially harm us if we come into contact with them. Then the products of fission are unstable nuclei that will emit beta particles. And also, most of the energy from the fission will be released as gamma rays, which can harm us if we come into contact with them. For obvious reasons, people can't go into the reactor while the fission reactions are happening. Then we also surround it with walls of thick concrete that can stop all kinds of radiation from escaping, even the highly penetrating gamma rays. But what's another key safety feature that reactors have to use? The control rods are used to control the rate of chain reactions. Now, these are different from the fuel rods since they don't take part in the reaction. We can also move them in and out of the reactor during the reaction. Here we see some of the control rods that have been raised out of the reactor, and here some that have been partially lowered so they fit between the fuel rods. These control rods are made from boron, which absorbs neutrons. But how does this affect the rate of the reaction? Well, first remember that we arrange the fuel rods like this so that the neutrons released during fission can be transferred between them and cause chain reactions. A fission reaction in one rod will lead to a reaction in the next. However, if we position a control rod between the fuel rods like this, then this partially blocks the paths that the neutrons could take between the rods. This means that some of the neutrons released by fission in one rod could be stopped before they cause a chain reaction in the next rod, since they get absorbed by the boron control rod. Limiting the number of neutrons causing chain reactions is important, since remember that fission reactions can potentially cause 2 or 3 chain reactions and make the rate of reactions spiral out of control. So it's best that after a certain point, we make sure each fission reaction only causes one more reaction. But what if we want even less reactions to happen? The reactions slow down when more rods are lowered into the reactor or rods are lowered down further. If we add more control rods, then that means there are less fuel rods that neutrons can freely move between. And then if we move control rods further down, this limits the space for neutrons to move between rods even more. So overall, this means that more neutrons get absorbed by the control rods and fewer chain reactions occur. But what if we need the reactions to stop entirely? In an emergency, the rods are lowered all the way into the reactor to stop the reaction completely. So if, for example, we notice radiation leaking from the reactor, or some machinery is overheating, then we could quickly drop the control rods all the way into the reactor. This means the rods now completely block off the paths between the fuel rods, and all neutrons released by fission reactions will be stopped from reaching the next rod. Then, with no way for the fuel rods to receive neutrons to undergo fission, the reaction will end. For your exams, make sure you can explain both the safety features we've looked at and why they are important when designing a fission reactor.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!